Threads in Java interact a little differently with the garbage collection system than most other objects. They have multiple criteria for when they're available for garbage collection. They must be unreachable through references. This is true for any object. And they must not be running, meaning that their run method must be completed or they were never started at all by the time they got to being unreachable by references in the program. So here's an example, a class called ThreadGC. It's got a GC method that's its, cleaning method here that announces the garbage collection is being done. It requests of the system to do garbage collection and to run finalize methods, and it then sleeps for a second. Now remember, this is a suggestion to the system, but it ought to get around to it eventually. Then we have a main that creates a new thread, new running thread that runs for 20 seconds. It's just passed a parameter and told how long it should run. And then that thread is started. And then we create another new running thread that runs for 1 second. It's started. You'll notice we lost our reference to our original t here when we said t equals some new thread. So for most objects, they would be garbage collected shortly after this line where t no longer points to the thing that it used to. Then we call a loop 3 times to call our garbage collection method. And then we remove the reference to our thread, the second running thread, and then we call the garbage collection one more time. So here's the code for running thread. It takes some amount of delay. It creates or it stores that delay, and then its run is going to sleep for that delay amount and then say that it's finished running. It'll tell you when it's started and when it's finished. And it has a finalize method that lets you know when it's gone, when it's being deleted out of memory. So we run that program, and it says that the thread with 20 seconds has started. We're doing our garbage collection, but nothing is marked or nothing is being deleted here up to this point. Now, when the thread with 1 second starts, we know we've lost our reference to the thread that was a 20-second thread. Then that 1 second thread finished running. We call our garbage collection method, suggesting over and over again that Java should do some garbage collection. But we notice that it hasn't garbage collected that thread that ran for only a second. And the reason why for that is because that thread doesn't lose its reference until down here, after the other thread presumably has finished and we are printing out that we're removing the reference to it. So the 20-second thread finished running. We do some more garbage collection. That one gets garbage collected first, even though its reference was gone first and its execution finished here. It gets deleted. I'm sorry. Its reference was lost earlier, but its execution lasted longer, but it's garbage collected first. Then we do some more suggestions of garbage collection. Then we finally remove the reference to the thread that took a second to execute. And now finally, after some more garbage collection, that thread is gone. Oh, and in case it's confusing, I want to point back that GC method actually suggests garbage collection and does its print 10 times. So there should be 30 of those total because we're calling to our GC method 3 times so that we can try over and over again the suggesting that garbage should perhaps be collected, and then within that we're suggesting it 10 times. So that's why it's printing so many times here. Even though our GC method is only called 3 times, it calls to the system's GC method and does its print 10 times each. All right. The other thing that can make garbage collection a little weird for threads is that threads can keep implicit references to objects, which prevent garbage collection as well. So here's an example. This class is called blocker because it's going to block garbage collection from happening or have its garbage collection blocked in some ways. So it's got an object called lock, and then we create a blocker taking some object O, lock equals O, so we've got a reference to it. This is an actual tangible reference. And then down here, we have block method that synchronizes on the lock and then calls wait and waits for some amount of time until it's notified, and its finalized will tell us that blocker is gone. We then have our thread class that extends thread. It's got a blocker object. It stores some blocker that's passed as a parameter. And then its run method will tell us the thread has started. It will call block, which is the one that synchronized on the lock object and then waited for a bit until it's notified. Then the tricky part is that the blocker could potentially be garbage at this point, but not before here because we're actually using it and we have references to it. But then the thread keeps running at this point. We sleep for 5 seconds. We say that the thread finished, and then we exit the run method here. The finalize for the thread will tell us that the thread has been garbage collected as well. Now you're going to wonder why I've stated that the blocker can become garbage here but not before here, and that'll become a little more clear as we look at the main method. So the main method does things that are a little weird here, and this is just to illustrate this particular point. We've got that object that's our lock, and we feed that to our blocker, which we feed the blocker to our thread. So these three are all connected. The thread has a reference to the blocker has a reference to the lock. We tell our thread to start, but it quickly blocks, right? That's what the blocker method or blocker class does, is it comes in here and it waits on its lock object. And so then we could tell our main thread to sleep for a full second, which really doesn't do much of anything because T is going to wait because its blocker is waiting on some notification on lock. We then, once we wake up from that sleep, we delete the references to the thread and to the blocker. This is arbitrary. Assume our program moved on and, created a new thread and did some new stuff. So we've set both the blocker within the thread to null. The variable is null. So there's no reference to this blocker that was created before. And then the thread also gets set to null, the thread variable, which means that there's no reference to this thread either. But remember, threads cannot be garbage collected until they have finished running, if they had been started at all. So we call to garbage collect, but that can't do anything to our blocker or our thread, in spite of the fact that neither of them has an explicit reference from anywhere anymore, because the blocker is still waiting. It's still in that blocking state. So this implicit reference, the thread is waiting because the blocker has caused the wait, and therefore the blocker can't be deleted because the thread also can't be, the thread is paused execution on a variable of that blocker, which makes some sense because when the thread resumes execution, it's going to resume execution inside of one of the methods of the blocker class. And so, of course, we couldn't delete that blocker object because when we resumed execution, we wouldn't know what to do from that point onward. So there's this implicit reference. Nobody has a variable toBlocker, but it's sort of referenced by the fact that the thread has to hold on to that object and all of the related fields and things like that to resume execution successfully. And that's exactly what it will do, is that it will take the lock on that lock object, and then we'll notify on that lock object, which will wake the blocker back up and resume execution here, which wakes this thread back up. It finishes the block method finally. It comes down and prints, thread is still running, after we've lost our references and after we notify. So all of these prints from here downward are happening after that notify line right there. Then the blocker can be deleted after execution resumes. It does not have to wait until the thread finishes entirely because there's no explicit reference to it, and there is it's not being held to resume the thread's execution, so that implicit reference is gone now too. So the blocker can be deleted before the thread finishes. Then the thread finishes, and now finally the thread can be deleted too. So the short moral of this story is that threads themselves can be a little confusing with garbage collection because they need to both have no references to them and no longer be running. And threads can also cause some ambiguity in other objects being garbage collected if the resuming of execution of that thread would require the other object to still exist. For instance, it's resuming execution inside of a method of that other object, or it's resuming execution based on a field, an instance variable of that other object. So garbage collection gets a little harder to predict overall when we're dealing with threads. It's not just based on references, explicit references. It's not even just based on execution. It can also be based on what's blocking at the moment as well.